All right, so video 2 here for 7.1, we're going to focus on the coordinate plane a lot more. If you recall from topic 3, a lot of our transformations are on the coordinate plane, so dilation is no different. So it says, what are the vertices of a dilation by a scale factor of 3 of this triangle ABC? So notice it says the notation D3 of this triangle ABC means that the image of triangle ABC after dilation centered at the origin with a scale factor of 3. So again, this is a big deal. When you just see the number next to the capital D, that means the center of dilation is the origin, okay? Which makes this problem very, very, very simple, okay? Here's the process, right? Right here. When you do a dilation by a scale factor of n on any ordered pair x, y, and the center of dilation is the origin, you are simply going to take that scale factor and multiply it with the coordinates. And that will give you the new image. Okay? So again, this is what you need to remember for a dilation about the origin. So let's take a look at each set of coordinates. So A is at 2, -1. So if I want to find A prime, I'm going to take my scale factor of 3 and multiply by 2. And my scale factor of 3 and multiply by -1, which means that my A prime is going to be at 6, -3. B is at the coordinates -1, 2. To find B prime, I'm going to take each of those coordinates and multiply by my scale factor of 3. So 3 times -1 and 3 times 2, which gives me the location of B prime at -3, 6. And then if I take a look at C with coordinates of 3, 0 on the x-axis there, to find C prime, I'm going to take each and multiply it by 3. So 3 times 3 and 3 times 0. That gives me a C prime of 9, 0. And there are the coordinates of my new image. Now I do want to graph these real fast. Sorry that I did not extend the graph enough. But I want to point out something about this idea of, center of dilation, pre-image, image. So A prime would be at 6. So 4, 5, 6, -3, 1, 2, 3. So there's A prime. B prime is at -3, 6, 1, 2, 3, 4, 5, 6. So there's B prime. And then C prime is way out here at 9. So this is 5. We'll say 6, 7, 8, 9. 0. There's C prime. So here's my new, I'm doing my best here, my new triangle. Not going to look pretty. There we go, right? So there's my dilated image. Okay? Notice that it got bigger. Should look about 3 times as big. Now, the one thing I want to point out again is this center of dilation, right, the origin, if you connect it to your pre-image, so if I connect it to A, and then I continue on to connect it to A prime, that should be in a straight line, right? That's very important, and that'll be the case for A, for C, and for B and B prime, right there, okay? So again, keep that in mind when you're doing this. If you want to take a quick check, you can always use Desmos. You can type in the polygon command, and you can type in these coordinates and see if you get that figure where you can see that line going through the center of dilation, the pre-image, and the image. Okay, one more coordinate plane one here. All right. It says, what are the vertices of this, right? A dilation scale factor of 1/2 about R, right? So notice here, right? Now we are going to dilate it about a center other than the origin, right? So first thing, if R is a point in your figure, which it is, then R and R prime will be the exact same point. Okay, so R prime stays put. Okay. And now what I'm going to do here is I would use horizontal and vertical counting, right? So, this is a rectangle, so the sides are nice, so I can just count one direction. But if I was using a triangle per se and they were diagonal sides, I would use my rise and run, which should be in the same proportion as you go through. So for instance here, I want to go Q. Where's Q prime going to be? Well, I'm going to count how far it is from R to Q. From R to Q is 1, 2, 3, 4, 5, 6, 7, 8. So from R to Q, is a length of 8. So to find the distance from r prime to q prime, I need to take 1/2 the scale factor of rq. Well, that'd be 1/2 of 8, which is going to be 4. So from r prime, we're going to count 1, 2, 3, 4. There's where q prime is going to go. Same thing with s. I'll do s because it's horizontal. So r to s was a length of 1, 2, 3, 4, 5, 6. So then r prime to s prime will be 1/2 of that length, which will be 1/2 of 6, which is 3. And from r prime, I'll count 1, 2, 3. And there's s prime. And now what I was saying about slope is, okay, I know that t is going to be right here. I know that. T prime, because it's a rectangle, right? But if I wanted to find how to count from r to, r to t prime or r prime to t prime, I would count the slope from r to t. Go down 8 and right 6. So then I would cut that in half. I would go down 4 and right 3. And again, that gets me where t prime is. But again, because it's a rectangle, we should know the shape. And this is going to be your new figure, this rectangle. So it is not impossible to do dilations other than about the origin. Now it does want the vertices, so I'll quickly label them, right? So r prime is still going to be at -2, 7. Same place as r. Rq prime is going to be at -2, but it's at 3. T prime is at 2, 3. And s prime is at, oh, I'm sorry, t prime is at 1, 3. My apologies. And then s prime is at 1, 7. And there we go. QRST, something like that, right? There you go. I put a parenthesis there. Okay. All right, so now let's talk about using scale factor, right, in this next picture. Okay, so it says, a blueprint for a new library uses a scale factor of 1 to 50. Mr. Ayer measures the reading space on the blueprint to find the actual dimensions and area so he can order future furniture. What are the actual dimensions of the reading space? Okay, so on this picture here, right, we need to label the blueprint dimensions. So I'm going to say BP for blueprint. So on the blueprint, you can see that by this ruler, we are 14 centimeters by 12 centimeters, right? So 14 centimeters by 12 centimeters. Now, we can use this scale factor of 1 out of 50, right, to find the actual dimensions, okay? Now, first off, scale factor is unitless, meaning that the top and bottom have the same units. So because this is being measured in centimeters, right, that's centimeters over centimeters. So the answer we're going to get when we do these proportions is in centimeters. So I want to kind of clear that up. So let's say I want to find, let's call this x and let's call this y, right? But on the actual dimensions, right? So we're going to set up a proportion. A proportion is simply a fraction setting, or an equation setting two fractions equal to each other. On the left side, I will put my scale factor, which is 1 out of 50. And of course, the 1 is going to be the blueprint measurement, and the 50 is going to be the actual measurement, right? So for every centimeter on the blueprint is 50 centimeters in real life. So now we're going to take this 14 centimeters, which is the blueprint length, put it on top, and I'm going to put my x on bottom, which is the corresponding length in real life of this reading space. We're simply going to cross multiply here, right? X times 1 is x. And 50 times 14 is going to be 700. And that would be in centimeters. Now again, if I want to cut that off and put it into meters, I would divide this by 100 because there are 100 centimeters in 1 meter. And if you divide that by 100, you get 7 meters. So this real reading space is going to be 7 meters long. And then to find y, I'll do it in blue here. I'm going to use the same proportion, 1 out of 50 equals, but now I'll put 12 over y. And we'll cross multiply, and you get y equals, and that's 600 centimeters. Again, divide by 100, and you get an actual length of 6 meters. So the actual dimensions of this reading space are going to be 7 meters by 6 meters. Okay, and one more problem involving this picture here on the next slide. So now it says, what is the actual area of the reading space? How does the actual area relate to the area on the blueprint? Okay, so actual area of the reading space. So a couple things, right? So if we take a look, area of a rectangle is base times height. So if we use the dimensions from before, I would do the 7 times 6, right? So 7 times 6, that's 42, that's meters squared, right? So that is the actual area. Now, if they want us to compare, and I'll do this in blue, if they want us to relate the two areas, then I don't want to use the meters. I want to use the same units as the scale up above. So I actually want to use the centimeters. So to do this comparison, I'm going to use the 700 centimeters by the 600 centimeters. And that's 420,000 centimeters squared. Now, I want to compare that. So that's the actual. So I suppose I should be doing this is the area actual. That's ACT. It's terrible ACT. Actual. So now let's compare the area on the blueprint. And again, the dimensions are here, 14 and 12. But if we do 14 times 12, that's 168 centimeters squared. So now let's compare that, right? Let's see how this is going to compare to this scale factor of 150. So let's put it in a ratio. So let's put the blueprint area on top and the actual area on bottom. So that's going to be 168 over 420,000. And these are both actually divisible by 168. So we can divide that by 168, divide that by 168. You could use Desmos to simplify it as well. Just make sure it's a fraction. You'll get 1 over 2,500. Now, if we think to ourselves, man, how does that compare to the scale factor of 1 over 50? Think about this 1 over 2,500. 2,500 is a perfect square. It is 50 squared. And 1 is also a perfect square. It's 1 squared. So it's 1 squared over 50 squared. Well, there's a rule with exponents that you can actually pull that squared out. So you could make this actually 1 over 50 squared. So this is actually a rule in math, geometry, about similar figures and their areas, perimeters, and volumes. So this actually is kind of a state standard. So I'm gonna again from here, I'm gonna say that this 1 over 50 squared is your scale factor squared. And I'm gonna write a little blurb somewhere, maybe off to the side right here. I'll do it in green. You need to know that the ratio of areas of similar figures is the square of the scale factor. Of the scale factor. Hopefully you wrote that somewhere better than right there, right? You have space, right? So the ratio of the areas of similar figures is the square of the scale factor. Okay? So keep that in mind as you go through. And again, the idea is that because each dimension in similar figures is multiplied by that scale factor, when you multiply base times height, you're actually multiplying that scale factor twice. And scale factor times scale factor is scale factor squared. So that's the quick and dirty version of why that is the case. Okay? Excellent. Thanks for watching, and we'll see you in class.